In this video, we're going to discuss working with multiples of pi over 6, pi over 4, and pi over 3. So we'll start with a unit circle and label the points specified by pi over 6, pi over 4, and pi over 3. We've established these coordinate values previously and learned that they represent the sine and cosine of these three angles. So for example, the fact that the y coordinate specified by pi over 3 is root 3 over 2 tells us the sine of pi over 3 is root 3 over 2. And we could similarly extract specific sine and cosine values just by using these angles and their corresponding coordinates. So what we're going to do is utilize the symmetry of a circle to try to find other sine and cosine values that are related to these three angles. So let's start with pi over 4 and just focus on that angle in our circle. All right, so what we can do is recognize that there are three other points in the circle that are related to this angle pi over 4. The point specified by pi over 4. There are symmetric points. Well, if we reflect this point into over the y-axis and over the x-axis, we find other points that have the same coordinates as the point in quadrant 1, except in some cases now those coordinates are negative because we're in quadrants 2 or 3 or 4. Now, if we can find the angle that specifies these 3 points, then we'll suddenly have access to a few more sine and cosine values. So let's start with this angle in quadrant 2. Let's figure out what angle is specifying that point, and then we'll know the sine and cosine values of that angle. Well, this angle that's represented in pink here, is almost a half trip around the circle. It's just missing this last part here, which is measures pi over 4. And so the pink angle must be almost pi, right? Pi is a half revolution. It would have been pi, but we've taken pi over 4 away from it, essentially. And so that angle ends up being 3 pi over 4. Oh, there's a little typo. 3 pi over 4. All right, so we know what angle specifies that point. So now we know that that point represents the sine and cosine of 3 pi over 4, the coordinates of that point. All right, so let's move down to the point in the third quadrant. So we know the coordinates of that point. We just need to figure out what angle specifies it, and then we'll know the sine and cosine values of that angle. Well, this angle is a half revolution. Half revolution, that's pi, plus this last part here, which is pi over 4. So we'll take pi and add pi over 4 to it, and we'll get 5 pi over 4. That's this whole pink angle there that takes us down into quadrant 3. And so now we know that the coordinates of that point represent the sine and cosine values of 5 pi over 4. And finally, we can move into quadrant 4 and try to figure out what angle is specifying that point in quadrant 4. Well, that pink angle that's taking us all the way around the circle, or almost all the way around, it would take us all the way around, except we're missing this last bit, which is pi over 4. It must be pi over 4, or else it wouldn't be a symmetric point with respect to the original first quadrant angle. And so the pink angle must be a full revolution, which would be 2 pi minus that last bit, pi over 4. And if we do this calculation, we'll get 7 pi over 4. And so we discover that this point, the coordinates of this point in quadrant 3, represent the sine and cosine values for 7 pi over 4. And when we step back and look at this situation, we see that all 3 points here represent the sine and cosine values of multiples of pi over 4. And all of these coordinates involve the number square root of 2 over 2. It just, in some cases, we have to make that number negative if we're in a quadrant where the coordinates are negative. So let's give this a try. Look at an example. Consider a somewhat unusual multiple of pi over 4, the sine of 19 pi over 4 and the cosine of 19 pi over 4. Well, because these angles are, this angle is a multiple of pi over 4, we should expect its sine and cosine values to be involve the number square root of 2 over 2. We just have to figure out what quadrant the angle falls in to determine the sine of that, of their sine and cosine values. So let's pull 19 pi over 4 off to the side and figure out how big it is. And it turns out, since 19 pi over 4 equals 16 pi over 4 plus 3 pi over 4, it equals 4 pi plus 3 pi over 4. And we know 4 pi is 2 full revolutions. So 19 pi over 4 is 2 full revolutions plus 3 pi over 4 more. So what we could do is rotate around the circle 1 full revolution and then another full revolution, and then we'll finish off 3 pi over 4. And turns out that we specify that point in quadrant 2. And we see that 19 pi over 4 falls in quadrant 2, so we know that the sine of 19 pi over 4 is the y-coordinate, square root of 2 over 2. And the cosine of 19 pi over 4 is the x-coordinate, negative root 2 over 2. And in a similar way, we could find the sine and cosine of all multiples of pi over 4. All right, let's come back to our first quadrant angles, and now let's focus on the multiples of pi over 3. All right, so we'll just isolate that angle, and let's use the symmetry of the circle to find the coordinates of 3 other points in the other 3 quadrants that involve the same numbers, 1/2 and root 3 over 2, but we occasionally have to make them negative depending on what quadrant we're in. Now again, if we can find the angles that specify these points, then we'll know the sine and cosine of those angles, because the coordinates of points on unit circles represent sine and cosine values. So we can start with the quadrant 2 angle, try to figure out what angle is specifying this point. Well, as we know, a half revolution is pi radians. This pink angle is trying to get all the way around, halfway around, but it's missing this part, this pi over 3 that's left over before you get halfway around the circle. So the pink angle is pi radians minus pi over 3, which turns out to be 2 pi over 3. So now we know that the point specified by 2 pi over 3 has these coordinates, negative 1/2, root 3 over 2. So now we know the sine and cosine of 2 pi over 3. And now we can go down into quadrant 3. In quadrant 3, we know the coordinates of this point that's related to pi over 3, but we don't yet know what angle specifies that point. And we can figure that angle out by recognizing that halfway around the circle is pi radians. And then this bit that's left over here after half of a revolution is another copy of the original pi over 3. So we're going to have to add pi over 3 to pi to find the pink angle, which is 4 pi over 3. So this angle here is 4 pi over 3. So the point that we knew the coordinates of is specified by 4 pi over 3. So it means that the coordinates of that point are the sine and cosine of 4 pi over 3. And finally, moving into quadrant 4. If we can figure out what angle is specifying this point, we'll know the sine and cosine of that angle. Here's a situation where we're almost rotating all the way around a circle, but then we don't finish off this last part of the rotation, which is pi over 3 radians. So the pink angle is a full revolution 2 pi minus pi over 3, which equals 5 pi over 3. And so we know that that angle there is 5 pi over 3. So the point that's specified by that angle is the sine and cosine of 5 pi over 3. And when we step back and look at this picture, we see that all of the points that are symmetric to pi over 3 happen to be specified by multiples of pi over 3. So when we learn the first quadrant's coordinates, the coordinates of the point specified by pi over 3, we can use those to find the coordinates of multiples of pi over 3. It just have to make the numbers negative sometimes, depending on the quadrant we're in. So let's look at an example, an unusual multiple of pi over 3, 16 pi over 3. We should expect it to be related to pi over 3, but first we need to figure out what quadrant it falls in to determine the signs of the sine and cosine values. So we can pull 16 pi over 3 off to the side and recognize that it equals 12 pi over 3 over plus 4 pi over 3. And 12 pi over 3 is 4 pi. And that's 2 full revolutions. And then after 2 full revolutions, we add 4 pi over 3. So we could try to plot this angle on our coordinate plane by using 2 full revolutions. There's 1, there's 2, and now we rotate around 4 pi over 3, which is 3 pi over 3 pi, plus 1 more pi over 3. So it looks like it's aiming us into quadrant 3. And now we know that 16 pi over 3 specifies that point in quadrant 3. So we can determine that the sine of 16 pi over 3 must be the y-coordinate of the point, negative root 3 over 2. And the cosine of 16 pi over 3 must be the x-coordinate of that point, negative 1/2. And in a similar way, we could find the sine and cosine of any multiple of pi over 3. The numerical values of the sine and cosine values will come from the quadrant 1 information, will come from pi over 3, and then we just need to make those values negative if we're in a different quadrant. Alright, so we can return to our unit circle. And now we could focus on pi over 6. Alright, so we'll follow the same pattern here. We'll consider all the symmetric points related to pi over 6. It's easy to find their coordinates because we're just reflecting that first quadrant point into the different quadrants. And we know that the absolute value of the coordinates will be the same. Root 3 over 2, comma 1/2. We just need to make those numbers negative when we're in various quadrants. So let's start by focusing on the quadrant 2 angle. If we can figure out what angle this is, then we'll know what the sine and cosine values of that angle are. What's left over after this pink angle is pi over 6. That's how we get this symmetry. Has the same, that what's left over is the same size as the original angle, pi over 6. So the pink angle is almost a whole half revolution, which is pi. And we're subtracting away from pi over 6. And that turns out to be 5 pi over 6. And so the coordinates of that point represent the sine and cosine values of 5 pi over 6. Okay, and now we can go down into quadrant 3, figure out the angle that's specifying this point. And this angle will be a full half revolution plus what's left over after the half revolution, this little bit here. That's an extra pi over 6. So a half revolution is pi. Then we add to it pi over 6. And that turns out to be 7 pi over 6. So now we know that the coordinates of this point in quadrant 3 represent the sine and cosine of 7 pi over 6. Finally, moving into quadrant 4, figure out what angle this is. Well, what's left over after this pink rotation is an angle of measure pi over 6. And so the pink angle is a complete revolution, 2 pi radians, minus that pi over 6 that's kind of left over. And if we do this computation, we get 11 pi over 6. And so we realize that that point in quadrant 4 is representing the sine and cosine of 11 pi over 6. And we see that all of the multiples of pi over 6 have very similar sine and cosine values. They have similar sine and cosine values as does pi over 6. The only difference is that sometimes we have to make these values negative because of the quadrant we're in. So we could give this a try with another example. Sine of 23 pi over 6 and the cosine of 23 pi over 6. If we can figure out what quadrant the angle falls in, we can then extract its sine and cosine values. So we pull 23 pi over 6 off to the side and realize it's 12 pi over 6 plus 11 pi over 6. So it's 2 pi plus 11 pi over 6. 2 pi is one full revolution, so we'll go around once and then finish it off with an 11 pi over 6 rotation. So we have one full revolution, and now we go around 11 pi over 6, which is almost a full revolution, but we end here in quadrant 4. And so we see that that angle, 23 pi over 6, specifies the point root 3 over 2 comma negative root 3 over 2 in quadrant 4. So we know that the sine of 23 pi over 6 must be the y-coordinate of that point, negative 1/2. And the cosine of 23 pi over 6 must be the x-coordinate of that point, root 3 over 2. And in a similar way, we could find the sine and cosine values of all the multiples of pi over 6. They're all going to be involve these same two numbers, root 3 over 2 and 1/2. We just need to make them negative if the angle falls in a quadrant where the x or y coordinate is negative. All right, so now we're back at these are our three friendly angles in quadrant 1. And what we've discussed here in this video is that we can use that information in quadrant 1 to find the sine and cosine of all these angles that are symmetric to these angles in quadrant 1, that have a relationship with these angles in quadrant 1.